Hi, everyone. So it's 11 a.m. now. We're probably going to wait a few minutes for people to come in. So we're going to start around 11:03. I'll see everyone very soon. Hi, everyone. So we're just giving people a few minutes to trickle in. We're going to start in a few minutes. Hi, everyone. Really excited to be here today. For those of you who weren't here last week, my name is Luiza, and I'm a graduate student in the lab. And today, Ian and I are going to be talking about statistic and programming in R and Python. So we're going to have the chance to introduce ourselves in a second. I just wanted to give some information about today. So similarly to last week, there will be some links throughout the presentation. Those links are not there, so you have to like manually copy them or anything like that. We'll be able to send you the slides and the with the links later on. So those are just for your reference. Another thing that I wanted to say about today is that this is not going to be like a coding workshop where because we won't have the time to do like a crash course in coding in just an hour on like two different languages. So we're mostly going to expose you to the different things that you can do with R and Python and why we think it's important to learn these skills as a psychologist. And yeah, like any other talk in this series, please feel free throughout to use the Q&A function in the chat, and we'll be happy to answer your questions. We'll be able to answer some of your questions throughout, and then we'll see how time is, and we'll leave some questions for the end as well. Great, so let's get started. So just talk a little bit about my background. I got my BA from Swarthmore College. I'm originally from Brazil. I came here for college. Swarthmore is a really tiny liberal arts school in Pennsylvania. Then after finishing college, I worked as a behavioral research fellow at Kellogg School of Management. It's Northwestern's business school. And then I joined the lab here at Stanford a couple of years ago. This is like pre-COVID picture of our lab, so it's slightly not updated yet. But yeah, so I just wanted to say that kind of like my trajectory to learning coding skills, I did not like I had one class in college that had R, that tried to teach us R, but it was really not the focus of the class. It was a statistics class, so they would basically give us the code and we would run it. Which so yeah, I didn't really learn how to use R until much later. I started using R when I was working at Kellogg, because that was the language that they used. So there was a lot of, on my part, just kind of a lot of Googling and kind of learning these skills as I went. So if you're, a senior in college and you feel that you hadn't had the chance to learn these skills yet, I think that's totally okay. Um, and one thing that I said last week, and I think it's applicable to this week as well, is that sometimes looking retrospectively like this into my path from college to graduate school, it looks like a pretty straight line where, I got a BA in psychology. I worked in psychology for 1 year, and then I went to graduate school in psychology. But a lot of it was kind of like this, where, and I know this is like a cliche image, but I think it kind of does represent this experience of being kind of not entirely sure what skills I needed to go to graduate school. Like I applied straight out of undergrad and like didn't get in anywhere. Try to apply to a bunch of full-time positions, and it was difficult. So I think that in this series as a whole, we try to share things that kind of like helped us along the way. And I do think that learning how to code really helped me personally. Yeah, to just really expand the things that I could do, and on the way, kind of learning that I really enjoy doing it. So I hope this is the case for a lot of people, because yeah, I think it's a super cool tool, and I think that as you learn of how much you can do with it, it really becomes like this whole new world. Um, Great. So I'll send it over to Ian.
Hey everybody, good morning. I did not animate my slide as nicely as Luiza did, unfortunately, but yeah, similar in trajectory. This looks pretty linear, but it was very much not the case. So I earned my bachelor's in psychology from Virginia Commonwealth University in 2015. And then I was bouncing around and playing in bands and working at a grocery store for a couple years before I went to grad school. Didn't have any programming skills, had pretty limited stat skills. But got into NYU's master's program, 2 years there, graduated this past May. And then I was very fortunate to end up in the position I'm in now, which is lab manager of the Stanford Social Neuroscience Lab. So I would fully concur with Luiza that, these things look pretty linear, but they're often not. And our goal today is just to, kind of help provide some insight into learning more about programming.
Yeah, great. So how we're going to structure this talk today is I'm going to first talk about R in the first half, and then Ian's going to talk about Python in the second half. Great. So I'll start us off with this question, like, why should a psychologist use R? Because, like, I think we all know that there are a lot of like point and click interfaces out there that do the job most of the time, and that people find them sometimes more intuitive to use. So like, why should you spend the time trying to learn R? So just as a roadmap, this is kind of like how I structured the talk. So first, I'm going to talk a little bit about why use R. The second thing is the differences between R and SPSS. Full disclosure, I've never really learned how to use SPSS. I think like R was kind of like the main tool that I learned how to use for analysis. So I have a fairly superficial view of SPSS. So if you feel that I'm like not accurately representing what the full power of SPSS, forgive me. But this is just talking to people who use it more than I do. And then the third thing, which I think it's the most exciting part, is just showing you how powerful R can be in terms of creating really stunning visualizations, things that you see in places like the New York Times, where they have these beautiful maps and like beautiful figures, and how you can create it with just a few lines of code. So first off, like, why use R? Well, first, it's free, and I guess we can all agree that that's a really good thing. So it's a good thing not only because you don't have to pay for it, but also because being free allows it to be kind of updated more regularly than proprietary software. So I'll talk throughout this talk about how R really empowers users to be kind of co-authors of the R language. Like, people can create packages and really extend what R can do. And this just allows R to be constantly updated, which is amazing because it really expands the things that it can do. The second reason why is that it's popular. And this is really allows you to collaborate with a bunch of people who are using R, and allows you to, have this common interface. And it's becoming very popular in psychology. The third thing is that it's really flexible. And the fourth thing, which is really important, is that it promotes reproducible research. Using a point and click interface sometimes really hides the things that you're doing, while using R, you have like a literal like recipe of everything you did. So another person who wants to get a similar result should be able to just run your code and get the exact same numbers that you did. Great. So expanding a little bit more about what, it's not only R itself is free and open source. Anyone can go and download R, like, as soon after this talk is over. But also many of its learning resources are free. So Hadley Wickham, who really, deserves a lot of shout outs, is a person who created a lot of the packages that we use in R that made it so powerful. So he created the tidyverse that allows people to wrangle data, and the ggplot that allows people to analyze data in such, powerful, concise ways. He studied to be a statistician. He got his PhD in statistics, and then went on to like really try. And he realized while getting his PhD that a lot of things that people struggled with is just getting the data in a format that allowed them to analyze it. So he like kind of dedicated his life to, create this free packages that would allow people to do that. And he's really, now he works at our studio, and like his mission is to make code and these statistical tools accessible to anyone. So he also wrote this book called R for Data Science, which is available online for free. And it's really great because it's online, it's constantly updated too. So as new packages come in, he'll go and update how to use them. So this is a really amazing resource. I put some links here to other resources. So he also created a like advanced R book for people who want to go kind of like above and beyond, and a free resource for an R bootcamp. And you can find a lot of these online, like just Googling like free resources for learning R. You can find a lot of great places to start. The other thing is there's some, if paid resources that are also pretty good. Like I use DataCamp quite a bit as I was starting to learn. I thought it was helpful. I thought it was helpful maybe to a certain extent, because they try to make it so, you have access to, like you do these little modules. And I feel that after a while, it's just really helpful for you to have like a project of your own where you can have all the steps. But I feel as a starting point, it was pretty helpful for me. Great. So the next point is that it's popular. So this is just like an index for popularity of coding languages over time. And you can see that R has really been growing popularity lately. I would say, yeah, it really took like psychology, a storm. I feel that like a few years ago, at least when I was in college, and maybe it's because I was like in a really small college, but I feel that using R was not the standard. But then as soon as I left college, it just seemed like everyone was using R, especially the new generation of researchers. So why this is important is just like easier to collaborate if you're all using the same language, so Dean and I, who's another person who gave a lot of talks here in this series, like we've been collaborating on a project on COVID, and it's just really easy to like send code back and forth, and we can all understand. We have this common language that we can all understand, and it's pretty transparent, everything that we did to the data. Another reason why this is great is that there's a great community of users who are really motivated to improve existing packages and provide consistent online support. So I feel that R is a great community where like they're really eager to answer questions. Like there's a pretty big following on Stack Overflow, or it's this website that you can go and ask questions if you're stuck on your code or if you're getting an error message. Hadley Wickham himself is like really great about, like, he has a great presence on Twitter, for example. So if you follow him and you follow some other people in R, you can get like exposure to new packages coming out. And they're usually very, like, just a very nice group of people overall. And one thing that I will talk more later on is just that the development of the add-on packages have been very beneficial to social science scholars. So there are all these packages that allow you to like do Twitter scraping if you want to study language using like social media, um, or packages related to, like, there's like a psych package where you can do like get like mediations, figures, pretty easily, with just like a line of code. And so all of this really expanded like what we can do as social scientists. Yeah, another thing is that it's very flexible. So one thing that I really like is that it's very easy for you to update. Like, you just change like one thing and the whole rest of the stuff like remains the same. While like in SPSS, you would have to like click a bunch of times to redo all the steps that you did. So for example, this is like the first like block of code in pretty much any of my R files. So I am basically loading my library. So these are the packages that I want to use. And then I have my data sets. So for example, if one of these data sets, so here it says spring 2020, let's suppose that now I want the data for spring 2021, right? Because that has been updated. I can come here and I just change the one, if this is of course how the data frame is called. And my code, given that these data sets have the same variables, they're just updated, should run the same. So the only thing I need to do is just change it right here in the top of the file, and then I can run everything like I did before, which saves a lot of time. The other thing is that RStudio provides this interface that allows you to integrate a lot of things at the same time, and it's much more user friendly than just typing things on like a console. Um, so this is how RStudio looks. So you have like this place where you can write your code. You have your console where you get the output of your code. Um, you have this workspace where you have like your data files that have been loaded, and here you can have things like plots, or if you want help, if you need a function that you don't really know like what view does or what summary does, you can write question mark summary, and then you click that, and then the help page will open and it will give you the documentation for that function. So I just find that this flexibility of having all these things in the same environment is super great for a person who's just kind of like learning how to code. And one of the things that I love the most about R is this file format called R Markdown. So R Markdown allows you to embed everything in one document. So you have like code, text, and output, and it's all in one place. So this is kind of like, and I'm going to show you one of my R Markdowns in a second, but this is kind of like what it looks like. So you have this page here, where is the R Markdown, and you have, like here they're saying introduction, and they have a bunch of text, and then they have these gray areas, which is where the code actually runs. And here they're plotting like this pressure plot. And then there's this thing called knit right here. And at the very top of your R Markdown, you can specify if you want the output of your R Markdown to be a PDF or like a web page and whatnot. And then you can basically run knit, and it knits the document, and this is what comes out. So then you have this really nice like HTML page with, here like they made introduction big like bolder, because of the title, and then they have like the text, and then they have like their figures. So what this can do is people can write their whole papers, like a whole manuscript, on R Markdown. And it's really amazing because it really saves you time from, if you're doing things in SPSS and then you're like, oh, like something changed, like you talk to your advisor and now you're supposed to like not not include people who fail an attention check or whatever. And then you would have to like manually input. You have all these nice tables that were in your final manuscript, and now you have to basically change manually all of those numbers. Like, that's really painful. While here you literally just press play and the whole thing will update, and you have a whole paper updated. So everything, it really saves you from like the error prone method of like copy and pasting things and like changing things manually. So is just a super powerful tool. The other thing that I will say here, and this is not, of course, just for R, but I feel that for me, R has really enabled me to um, conduct research with like existing databases. And you could claim that you can do this with any language. You can do it with SPSS as well. A couple things that I do think are kind of interesting for R is that you can, for example, have set your data frame to be a URL. So you can, for one project, I was looking at Medicare data that was available online, and I know it changes like every year or whatever. So I can put my data frame to be a URL. So I'm only getting the most updated version. So whatever happens to it, and they like update it because they got new data, and I'll always get the most updated version. And then again, I can just run my code as I did before, and I don't have to redo anything. So that's super great. And I think for many of you who, like last week we were talking about applying to graduate school, and some people were concerned that they didn't have enough like research experience. Some, there's papers in psychology that are just run by using existing data sets. So you have data sets like the World Value Survey, the GSS, the American Action Election Studies. They have the census data, and I'll show you some graphs that I've created using these open data sources. But you can literally download this, wrangle it in R, create some visualizations, and you can talk about it. If it's something that you really care about and that it's related to your research interest, you can talk about it in your personal statement. You can say that, like that you did all these things with online. You can even be a paper, right? Like some papers in psychology are entirely using open data sources. If you want to even have like your replicability project yourself, a lot of the data for psychology now is online for a lot of the papers that you see out there. So you can see if they have open data, and you can run analysis. You can either try to replicate their findings, or you can run your own analysis with variables that maybe they didn't look at but you're interested in. So I feel that R really like kind of, for me personally, just opened up this new world of things that I could do. And I'm going to show you soon some of the things that I've done so far. But there are packages. It's so powerful because you have all these packages that, you can, as I said, that you can do some Twitter scraping, you can craft interactive maps, you can run sentiment analysis. Now you have packages even to run like more like fancier, like word embedding models in R. And it is the barrier for entrance for R compared to other coding languages, I would say, is lower because it's fairly user friendly. Like these packages really help in terms of having you to, you don't have to write all these like super long for loops for everything. You just have to know the right verb. And then you can really, just call that verb. Great. So as I said, kind of, I think this is the last thing about why to use R on that section, is that it promotes reproducible research. So it really allows for transparent data handling, which I find incredibly important. So your entire analytical plan is documented. So you have a literal script of everything that you've done. And, these common data wrangling visualization tasks are super fast, they're dependable, and they're highly replicable. And as I said, the use of R Markdown, for example, reduces errors associated with manual data entry and inclusion of outdated figures and tables in your final manuscript. So what this allows you to do is that for a random person who has your data, they're allowed to, do the same thing you did and not get a completely different result, which I think most of us know that this is something that is really crucial for the advancement of science. So I feel that that's like a really strong reason for why to use a coding language like R. Okay, so now we're like to the second section of R versus SPSS. Any questions so far?
I do have one in the Q&A. So we have a question: can I create a Qualtrics survey and send it to people?
Can you create a Qualtrics survey and send it to people? So yes, so that was not necessarily related to our analysis, but yeah, Qualtrics allows you to create surveys and share them with whoever you want. and you can easily download those responses into R and analyze it. So that's what I do all the time. So most of my work is running Qualtrics surveys and yeah, and analyzing it in R. So that's kind of like a really standard way of doing kind of social science.
Yeah, just to clarify, Qualtrics is a separate entity than R.
Mhm.
So you couldn't necessarily create a survey in R, but like
Oh.
Luiza said, you could definitely analyze it. And then one more question is: Are Markdown available through RStudio, or do you download it separately?
No, it's available through our studio. So yeah, you can basically go to like I believe is file, and then they give you different options. And like one of them is script, which is kind of like more of a bare version of where everything is just code. And another option would be R Markdown, where you have, and even when you just open a blank one, R is pretty nice, and it gives you like a good example of so it has like the text and the code chunks. So you can learn how to do it yourself. And there's this really helpful cheat sheets online on everything related to R. So like there's a whole R Markdown cheat sheet that tells you exactly how to like embed like output of your code onto the text file, how to like make the labels like in bold, like yeah, anything you want to make it look as a PDF or something like that. You can look at those cheat sheets, and it has a bunch of information. Okay, cool. So moving on to kind of this more explicit comparison between R and SPSS. So I would say, and I know this is kind of like a controversial claim, but I do think that it's easier to use R, and that's mostly because you can load data, pre-process it, and run statistical models in just a few lines of code. While it takes like 20 clicks in SPSS. And I know that people say that like, especially when you're teaching it to undergrads, that maybe it's too much to teach us statistics and like a coding language. And I agree that it may be, a little tricky to do both. But I do think that sometimes people undermine the learning curve for SPSS. Like you need this like super well annotated like screenshots, of like where to click, where to go. Like one wrong click, you can get the wrong data, the wrong results. So I do think that once you learn R, it's just like it's an easier platform to use. Um, as I said, reproducibility, it keeps a record of everything you did. There are ways of doing that in SPSS. I just don't think they're common. You can get a script from SPSS, but most of the time people are clicking, and then it's really hard for you to know what exactly was your clicking patterns. And there's no record of that. And sometimes also it requires people to like change things on an Excel file, so like manually change things before inputting the data into SPSS, and then that's really, there's no record of what you did, right? Like of how you, like what do you renamed it to. So it's just like easier also for yourself, right, in the future, if you wanted to like run the same analysis, to have something that is a complete record of what you did, instead of trying to remember all the steps that you took in order to analyze that data. Learning speed, I'll probably SPSS, people do learn it faster. As I said, although like I think learning coding language can be intimidating, our programming is fairly user friendly. All the packages do like make your life way easier. And one thing that I really like about R is that it's not a black box. I think you can use SPSS as a black box, where you're like, I input the data, I click here, and then I get what I want, but you don't really understand what is happening behind the hood. While with R, you really, you need to understand like, what format is my data in? Is it in long format, wide format? Like, like what kind of, it just requires you to know a little bit more, which I think it's a really positive thing. And I don't know if there's a bullet point here, but I think it speaks to the flexibility of it as well. Like you can do way more things in R than you can do in SPSS. Like we said, things like natural language processing, things like that would be hard for you to do in SPSS. Okay, so now we move to my favorite part, which is that R is super powerful. So this is just like a graph that I created using some data that I collected. And this is not a stunning graph, but it's pretty, like, it has, presentation quality graph that I created using very few lines of code, where, I have a title, all like I labeled the axis. I got this bar here that said the p-value of these differences. And this is, like, once you get the hang of it, is very easy to do. And I can just, for example, if I had, this is one DV, desire for cooperation across party lines, then I had another DV that was like effective polarization. I can literally just, like, change the variable up top and then change my labels in the same, and run the same graph, and just have it like this standard graph throughout. And there's a lot of things that I won't get into today, but R allows, like, ggplot, which is the visualization package, allow you to really customize your plots in whatever ways you want. Like, there are packages that will make them look like a New York Times plot, so, like, super attractive, like colors and backgrounds. You can make anything like bold, or like make these like different colors. It's really it's endless, all the customization that you can do. Yeah, so here we're getting at the thing that I said, where you can just like download data, like open data sources online, and create visualization. So this is something I did for, like, I just looked at like population data and projections for different continents using the World Population Prospects data. And so here, like, I created these bands that correspond to either the larger bands is 95% confidence values, and inner bands are 80%. So yeah, so like basically we see that, like, you know, in terms of projected population growth, that like Africa has been really has this really steep curve, while Asia, it's kind of like this, big growth so far, but it's projected to kind of like stabilize and decline over time. Um, so yeah, and I did this graph with, like, this is literally the code that I use to do it. So you can see, like, it might look a little intimidating, but it's really not. Like, it's not like 15 pages of code, right? It's just like a code block that fits into like this space, can create a graph like this. So this is another, this is not mine. So this is another graph that was created by, so the Open Science Initiative was trying to replicate a bunch of studies, right? Like a bunch of studies that were published in psychology. And what I love about this graph is that, first, I find it like really attractive. Second, I think that it conveys so much information. So here we can see that the colors are related to the p-value. So if p-values were significant versus not significant. On the x-axis, you have original effect size, and then the y-axis, you have the replication effect size. Then you have these density curves to show you pretty clearly, like, the difference between these two, right? Like here, you see that the original effect sizes were all like pretty much significant, and you have this density curve around like 0.25, whereas the peak. While here, when we were trying to replicate these effect sizes, you see that the p-value here, there's like really a spike around p-values that are not significant. And then they also made the dots be related to the replication power. So you basically give less weight to those replications that have really small powers, like reduced power, versus the ones that have, like 0.9 power to detect an effect size. So yeah, so I just feel that, like, you can do things like this in R that convey like so much information, and a lot of it relies on its flexibility and how you're able to customize things. Yeah, so this is something that I want to talk about that is based on what I said. Like, you see sometimes some graphs like this online, and you think they're interesting, and you can definitely try to do something similar with R using the open data sources. So I saw this, I think it was published in the Washington Post, but it was a pretty famous graph where it looked at drug overdose deaths in the United States, kind of like the opioids crisis. And it has this difference between 1999 and then 2014. So I was interested in seeing if the distribution of pills for opioids in this counties would reflect the overdose of deaths, death overdose. So basically, I was able to create this graph, which, you know, I use the same color scheme where I looked at number of pill distributed per person per year around all these counties, and from 2006 to 2012. And we can see that the, you know, kind of like Appalachian area over here tends to have a higher density of number of pills that were distributed per person. So I basically correlated it with basically opioid pills distributed per person and overdose deaths, and we see that there's kind of like this positive correlation between these two things. So yeah, so I basically saw these graphs, you know, online, thought they were interesting. I was taking a class at the time that really encouraged us to do this kind of project, and I was able to download the data and investigate a little bit deeper about, you know, oh, like they looked at this variable, can we look at this other variable and look at the correlation between the two? So yeah, again, did all of this in R, data wrangling and visualizations and the graphs, including the map. And I think that I can show you now. So I'm gonna change my sharing screen to be my R Studio, because you're also able to create these cool maps. Ian, can you give me a thumbs up if you see my R Studio page, just to make sure I'm sharing the right thing? Okay, great, thank you. Great, so yeah, so here's our markdown. So this is what I talked before. So you see that there's my console is here, which is giving me the output for my code. Here is everything. So basically I have these code chunks, and then I have some text. I have all my data files open here, and here I have the help viewer, but it can also be plots or packages or whatever you want. So for this one, I created these interactive maps. So here's the code that I used to do it. So again, really not, I'm using the leaflet package, really not a lot of code. And it's a map of London. So this, we're trying to look at cholera in this time in London that was pretty prevalent. They thought it was spreading through the air, but really when you look at the data, it seems to be due to these water pumps. So that's how they figured out that was spreading through the water. So I can zoom in and I can see the number of cases, and, you know, and kind of like see that they're around like this water pump, for example. So, and here I have like a broader graph, and yeah, and I can go literally anywhere here. I was just kind of focusing on this area of interest. And there's also, I created a heat map as well. So here you can see around water pumps. And again, you can kind of like zoom in and zoom out. And if I click knit, as I said before, it should give me, it should run all my code and then give me this nice HTML where it kind of looks like like a website, right? With, and I can click here, I guess, and it would take me to this area, and here, like, I can see my interactive maps. So yeah, so I just think that this is like just super, you know, powerful that we were able to do this with just a few lines of code and some Googling. You know, it's really great. Oh, sorry, I think you're still seeing my. Okay, great. So here, sorry. So this is the knitted document. So this is the HTML file where you can click on things and it changes. Yeah, it takes you there, and you can, you know, interact with the maps, and that looks like a web page that you could, you know, add to your website. So I'll go back to the slides if I can. Give me a second. Okay. Great. And then, yeah, the other thing you can do, which is pretty cool, is that you can create these animated maps. So here's a map for the interaction between GDP and life expectancy in all these different countries. And you can see that the relationship was always positive, but it's really been moving towards the the top of the graph here because GDP has been increasing and life expectancy has also been increasing. And again, really cool map, the really cool graph that you can make with just kind of like a few lines of code. So yeah, so hopefully I was able to convince you that it's a really great tool to invest some time in learning. And I just wanted to end by showing that you can even create some art with it. So there's these two artists that they use ggplots to create these like super cool like graphic art designs, Daniele Navarro and Thomas Pedersen. So yeah, so there's really unlimited things you can do. I think it really equips users to make it their own and just, explore. So yeah, so this is all I have for today. I'm happy to take questions now.
Thanks, Luiza. That was great. We've got a couple questions in the chat. So the first one is, when using data from other researchers' open source data, do you need to reach out to them or cite them as authors?
Yeah, so that's a really good question. So I think it depends what you want to do. So if you want to just look at, so a lot of times I'm like, oh, I'm interested in the relationship between social mobility perceptions and how much people support like welfare. And then I know there was this paper that looked at welfare and looked at something else, and I'm kind of interested to seeing that was not the main point of their paper. I'm interested in seeing the relationship between these two things. For me, it's just like a way of getting more information. So I go in and I analyze it and I was like, oh yeah, these things are very correlated, and it kind of informs how I design my own study. For that, you don't need to reach out to them because their data is open. So like that's, yeah, the point of open data is that you will be able to download and use it. If you're planning on publishing their data, then I would suggest reaching out to them. Unless the data is something that is, like something like the census or the American National Election Studies or things like that. They're just like really broad databases that anyone can use. But if you're using data that was collected by like some researcher somewhere and made it openly available, I think it's worth reaching out to them if you want to like publish on it.
Awesome. Next question. What's the difference between R and Jamovi, or have you heard of Jamovi, and what's your opinion? I haven't personally. I'm wondering if you have a different answer.
I have not heard of Jamovi.
I wish I had an opinion.
Yeah, I feel that I'm missing out. So I really, sorry, I can't answer that. I'm not super familiar with Jamoji, but yeah, I should Google about it.
Yeah, same on my end. Last question we've got here is, could you take that HTML file and put it on a server in order to make it accessible to the public using a browser, or does that require extra steps and setup?
Yeah, that's a really good question. I think it's fairly straightforward. I personally have never done it. I mostly use the PDF version because I'm just sharing with collaborators. But I do think it should be fairly straightforward to host it somewhere.
Yeah, I'd agree. Okay, cool. That's all we got in the chat.
Great. So yeah, thank you so much, everyone. So now I'm gonna pass the virtual baton to Ian, and he'll talk a little bit about Python. I'm gonna stop sharing my screen.
All right, I'm gonna start sharing mine. Okay, can you see that?
Yes.
Yeah, great. Hey, everybody. So sorry, let me just move okay, great. I'm going to take a similar approach to Luiza in that I'm not going to talk so much about Python syntax as I am kind of application of Python to the domain of psychology and neuroscience. For a more thorough introduction to Python, I do have a series of notebooks in my GitHub repo here that I'll include just basic like setup, syntax questions, things like that. There are better resources that exist, and I'll have those for you as well, but I just wanted to provide that. So the overview I'm going to cover today, we're going to talk about automated stimulus generation, scraping data from unconventional sources, which Luiza touched on as well, and then applying machine learning algorithms to psych and neuroscience. So let's talk a little bit about what is Python, first of all. So Python's a general purpose language. In other words, it can be used to write software and applications. Relative to other languages that are general purpose, like Java, C#, C++, Python utilizes really minimalist syntax. So it's very readable and it's very clean. It's also really great as a first general purpose language to learn because it's so easy to read. Excuse me. So in this snippet here, this is how you would print "Hello World" out to the command line in Java, right? You have to define the class. You have to tell the system what kind of object you're looking at. You have to define the function this way. In Python, you can really just do it in 2 lines, and you're going to get exactly the same result. So you can see, I mean, just compare and contrast. The amount of code you have to write in other languages is much more relative to Python, and you can retain a lot of the power that you get in those more general languages. So Python is built on this philosophy of, it's called the Zen of Python, okay? And some of the tenets include explicit is better than implicit, sparse is better than dense, and readability counts. And especially when you're learning how to code, I mean, all of those things are so true, especially once you've been coding for a while. If you can't read your code, you're going to have a lot of issues, right? So Python makes it really easy on us. So just comparing and contrasting Python and R a little bit. So R is really optimized for statistics, but it's not a general purpose programming language. So you couldn't write software with R per se. You couldn't make scalable production code with R. Python you can, and on top of that, you have above average statistical processing compared to Java, C++, excuse me, C#. So, long story short, Python can do a little bit of everything, and it can do it really well. So let's talk about automating stimuli with Python. So when I say automation, what I'm talking about is defining what we want to do and writing the program, and then just giving Python the keys and letting it do most of the heavy lifting. So say you were designing a psych experiment where you were comparing, 2 visual stimuli here. We have 2 faces. Python makes it really easy for us just to pair those up from single images, make a new JPEG or PNG file, and export it to a different folder in our on our computer. So I obtained all of these faces from the Chicago Face database, which is a really great resource I just wanted to touch on, because you get these really high quality images you can use for stimuli presentation, and it's completely open source. You just need to send them an email kind of with your goals and your research plan, and you can have access to hundreds of photos. So before we get going, I just wanted to define a couple things. So to accomplish this pairwise stimuli generation, we're going to need to write something called a function. So in Python, a function is a set or block of reproducible code, and we need to write it only one time, but we can use it ad nauseum, endlessly, really. So we don't have to write the same code over and over and over. And prior to that, we're going to import a couple relevant modules. Luiza talked about libraries in R. Modules in Python are exactly the same thing. Okay, it's just collections of pre-written code that we can just bring into our program to save us some time, so we don't have to write everything from scratch. So let's go ahead and import. And I just want to show you where these are living. So we've got 8 photos here from the Chicago Face database, okay, all single images. And then we have this output directory, which is currently empty, right? So let's just bring those into our program in a list, and we can see these 8 are the same 8 that we have on our computer. And I don't know about everyone in this meeting, but my ideal afternoon doesn't always involve sitting in Photoshop and pairing up faces, and it would take a long time, especially when we're talking about 56 total combinations of faces here, right? So it would take a long time to do this manually. So let's go ahead and define our function. I'm going to skip over the nuts and bolts here and just kind of want to let you know broadly what's going to happen. So we're defining a function called generate stims. It's going to take an image on the left and an image on the right. And it's going to kick out a pairwise image for us. So let's go ahead and define that. And now in a simple for loop, we're just going to go through, and if the left is not the same as the image on the right, so we obviously don't want to pair up the same image on both sides, we're going to go ahead and call our generate stims function on each photo. And we can see here that output directory is starting to populate. And it's going to go through and make all 56 images for us in a span of, I don't have a timer set, but maybe 5 to 10 seconds, maybe a little bit longer than that. But sure beats an afternoon in Photoshop, if you ask me. So let's just let that run, and we'll make sure that we have all of the images that we thought we would have. Oh, not a late one. Oh. Okay, 56 items. Yeah, so we're in good shape. Python did what we asked it to. So my takeaway here for you is that writing functions in Python lets us just use the same code over and over and over, and that replicability is a major asset for us. So let's talk a little bit about data from unconventional sources. So Python's a very flexible language in that you can use similar code to do really different things. One of my favorite things to do when it comes to getting insights from people in real time is just to scrape tweets, because anybody who's been on Twitter can tell you that it's not a perfect place, not by any stretch, but it's powerful in that you have users interacting with each other in real time, which is a pretty cool tenet of social media. So really all you need to do to get set up here is you need access to Twitter's API, and that's going to be Twitter's application programming interface. All you need to do is you can take your existing Twitter account or a new Twitter account and just sign up as a developer. It takes all of 5 minutes. And what that does is that gives you access to a set of credentials that you can use to obtain raw user data from Twitter. And a bit of an aside, but Python doesn't stop there with its access to Twitter. You can also build a bot. I built this bot all in Python. Took an hour or two one afternoon, and it just tweets nice things at people every morning. I have it on the server. So an aside, but something cool you can do with Twitter. Okay, so let's go ahead and package import. So the credentials that I have to access Twitter's API, I keep in a text file. So we're just going to read that in. And as long as we're able to access the API, it's going to tell us that we're connected. If we're not connected, it'll throw an error. So let's just see what happens. And we're in good shape. We're connected. So let's build this scrape function, okay? So we're going to take a keyword and a number, a quantity here. And the keyword is just going to be the search criteria. The number is going to be the number of tweets that we want to get. And like the last vignette, I'm not going to go line by line here, but essentially we're going to kick out to a data frame, which is a tabular data structure. Like you have a CSV or an Excel, it's going to have columns and rows. So let's go ahead and define that. And we'll search for the keyword psychology, and we'll grab the last 50 tweets. Okay, let's just take a look at the first 10. Yeah, so that's pretty cool. Shout out to Richmond, Virginia. Yeah, so we got the last 50 times that somebody's tweeted about the word psychology, and you can see here from the timestamp, I mean, this was a matter of seconds ago, really. So as far as a stream of user sentiment and expression, I mean, you can get very granular very fast. Just looking at the tweets themselves, you could strip these of characters and do natural language processing or a sentiment analysis. Lots of different things. My takeaway here for you is that Python gives us access to data sources that we wouldn't otherwise have access to. So let's talk a little bit about machine learning. Sorry, this thing is really in my way. We'll talk about machine learning in Python. So you might be asking, why would we want to use machine learning in psychology? That seems like more of a computer scientific approach. Machine learning really is just a broad term for applying predictive algorithms and models to qualitative or quantitative data. Some examples you might know are linear and logistic regression, and some you might not be familiar with are random forests, k-nearest neighbors, a whole litany of other machine learning processes. So in this example, we're going to talk about principal component analysis, or PCA. So it takes a data-driven approach to dimensionality reduction. What that means, very simply, is we're going to move from a data set with lots of variables to a data set with very few variables. And that's a process called decomposition. So once we're down to the low dimensional space, we're going to apply a k-means clustering algorithm just to parse out clusters or groups of similar participant response. And you're wondering maybe, why would we want to do this? Like, it's nice to have a lot of variables. And that's totally true, but a risk you run with high dimensional data is that it can be overfit, which in short, it basically means that you can make a model that has very good results to the data in front of you, but as soon as you apply it to outside data or new data, it would not perform very well. So we definitely want to avoid that. And if you happen to be math oriented, which I am not especially, then a good primer on PCA, I have linked here to a Medium article. Lots of pairwise distances and eigenvectors, and it gets very fine grained very fast. But that's there for you if you'd like it. So we'll go ahead and do our package imports, and let's just look at this data set. So we've got a number of variables here. It looks like 25. Which is not the most high dimensional data in the world, but 25 is certainly more than 1 or 2. So let's see what we can do with that. And we have over 52,000 observations here. So it's a very robust sample size. Just describing this data set a little bit. So the HSNS scale, or hypersensitive narcissism scale, has 10 items. And the Dirty Dozen scale has 4 measures each of narcissism, psychopathy, and Machiavellianism. And I already went through and pre-cleaned, so we don't need to worry about outlier detection or anything in this example currently. So let's just plot the correlation matrix. Okay, and it looks like generally, broadly speaking, we're residing between like 0.2 and 0.6 of a correlation coefficient for these variables, which is pretty good. What we want to avoid is seeing a lot of yellow, which means that we have a lot of multicollinearity or variables that are correlated to one another. And the reason that's a bad thing is that if you have a lot of explanatory power across a couple of variables, you might only really be measuring one factor, right? So we want to avoid that, but we're in pretty good shape here. So let's talk about the PCA itself. So the first step is just going to be scaling the data, and really all that means is performing a Z transformation on each variable. So we're going to account for the within feature variance. And when I say feature and variable are literally tomato, they mean the same thing. So just looking here, I mean, we can interpret these as Z-scores. So this is, negative 1.5 standard deviations from the mean. This is 0.66, et cetera. So we're going to boil this data set from 25 using PCA. And the reason I chose 2 is twofold, pun not intended. The first reason is that as you increase the number of components that you break your data into, you start to run into a signal to noise ratio problem where, say we did 5 components, by the time you get to component 5, you would have a lot of noise and it wouldn't be very meaningful. The other reason I chose 2 is just that it's a nice means of visualizing this data. 2 is a pretty standard 2-axis. So let's just see what we're looking at here. Great. So we have exactly the same number of columns, but you can see here we went from 25, rows, excuse me. We have the same number of rows and we went from 25 columns down to 2 columns. Now that's a little abstract. What does that actually look like? Well, if we just go ahead and plot it with a scatter plot, you can see here we have component 1 and component 2. So those are really just factors that are accounting for variance here across the data set. And it's important to note that PCA is an unsupervised machine learning algorithm, which means that we're not imputing a dependent variable into this a priori, right? We're taking in all the data and seeing what this algorithm does for us. So that's essentially what that means. So let's move on to the clustering component, because I think this is pretty cool too. I've selected 5 clusters here. That is not arbitrary. There is a reason for it. We use something called the elbow method, which you can see here. So K is going to be the number of clusters, and the distortion score here is essentially the pairwise distance from the mean to each point. So essentially what we're trying to do is create the optimal number of groups that are different, but also hold explanatory value as to those differences, if that makes sense. So we don't want, say we did like 15 groups, like it would be very hard to discern meaningful differences between them because there'd be so many. But if we only did 4, we wouldn't really have groups that were that similar in this case, right? So we ended up going with 5 when I ran the elbow method for this model. So let's just go ahead and see what that looks like. Drum roll. Okay, great. So we can see here we have the same exact shape of data, right? It's the same data, but it's split very evenly into 5 groups. I shouldn't say evenly, it's split very clearly into 5 groups, right? So we can, as we might in tune, these participants are qualitatively different in their responses than these participants. And now we have a data-driven approach to back that up. And I think this is all kind of abstract until we project these clusters back into the high dimensional space. So let's go back to our data set that had 25 variables, and let's take these group labels for each participant and just push them up to that high dimensional data and see, okay, what are we dealing with here meaningfully? What do these differences actually mean? And this difference between cluster 0 and cluster 1, I think, is pretty illustrative. So we have, and these are all mean scores, right, for each group. So, the average age for group 0 compared to group 1 is much higher. Gender and accuracy are comparable, a little bit different, but, not statistically so, likely. But then we start getting into responses on the questionnaire measures. And we can see that participants who were clustered into group 0 scored much lower on all of these than participants in group 1. So you might hypothesize, okay, there is some qualitative, difference here between participants who respond this way and participants who respond this way. So the takeaway here is that, machine learning approaches to solving these problems give us a really nuanced means of exploring data that's hard to do manually. It's hard to, we would have to run a lot of tests prior to understanding these differences. Taking an algorithmic approach puts us in pretty good shape. So the last vignette I've got for us is machine learning and neuroimaging, which is a really booming topic in the last 5 to 10 years, but it's really been exponential in the last 5 to 10 years or so. I should start with the fact that this is not an introduction to neuroimaging whatsoever. It's more just, kind of to show you what Python can do in that domain. So just a couple definitions before we dive in. So fMRI, for those of you that don't know, is functional magnetic resonance imaging. Okay, and we'll use it to measure changes in blood flow to and from neural regions during a functional task. We measure those in voxels, which are 3-dimensional spatial representations of a neural region. In a medical MRI, a high resolution MRI, you have upwards of 1 million voxels in the brain. We often don't want to have that many voxels included in our computations because, as I mentioned before, I mean, it sounds like a nice afternoon, but there's more to do. So to cut down on that computation time, we'll use something called a mask. So what that's going to do is just subset the voxels that we want to analyze. And that's actually a twofold benefit because it's going to help reduce noise in our analysis, as well as cutting way down on that computation time. And lastly, Nifty is just a file format that's kind of a standardized means of representing high-dimensional data from fMRI. And classification is a machine learning algorithm that's going to predict a target's class or group membership. And I've got a pretty digestible primer on fMRI attached here if you want to take a look. So everything we were doing in this vignette was in a package called scikit-learn, which is one of the preeminent machine learning packages in Python. We're going to use nylearn for neuroimaging. And it's actually, they were developed by the same team. So you're going to notice they're very similar. We're not going to go too far under the hood, but I just kind of want to show you what you can do with nylearn. So we're going to grab the Haxby 2001 data set, which is a pretty famous block design study from Dartmouth. They have a face versus object representation in the ventral temporal cortex. 6 participants, 12 runs, and 9 conditions. Sometimes they were seeing faces, sometimes they were seeing objects, etc. So a cool thing about nylearn is that it comes with data sets included, and scikit-learn does as well. So you can use those to practice and run different algorithms. Let's just go ahead and grab the first participant here from the Haxby data set. and let's just plot what it's going to look like. Okay, so this is not a functional scan. This is just kind of showing we have X, Y, Z. We're looking at three-dimensional representations of the brain. Okay. Let's go ahead and apply our mask. So like I mentioned, a mask is just a means of cutting down literally the number of voxels that we're going to look at. So we don't want to look at the hundreds of thousands of voxels here included. We just want to look at the ventral temporal cortex. So let's go ahead and look at that. And this is why we cut down to a masked number of voxels. So what we're seeing here is just signal response obtained from the MRI machine. So the shape of that, we can interpret that as we're down to 464 voxels. So way, way down from the hundreds of thousands that we would have been dealing with a full brain data set. And this first number here, 1452, is the number of scans in the study. Okay. So we're cutting way down. Let's just take a look at those first three voxels just to kind of see the time series. I'm talking about obtaining the signal here. Let's just see what that looks like. So this kind of, I believe, illustrates the functional nature of this task, right? So the first 74 scans or so are pretty harmonious in terms of neural activity, right? We've got kind of a similar trend line. And right around scan number 75, we see something really change here with this. I'm not sure if this is the first or third voxel, but this voxel here really changes, and this one stays about the same. So immediately we can start to say, okay, functionally, what's going on? Something's different. And again, here around 123. We're not going to analyze the whole data set, for time's sake, but just to note that the functional nature here is worth pursuing, worth looking into. So let's just go ahead and see the different presentation targets that the Haxby lab included here. So we've got all of the possible conditions that participants were in. We're just going to cut it down to human faces and cats. Only the best stuff here. So let's just go ahead and cut down our mask. So we were down from 1,400 scans down to only 216. Okay, but the same number of voxels. So we're still just looking at that ventral temporal cortex, but we've cut way down the number of scans that we're going to analyze. So to do this, we're going to do something called a support vector machine classifier. And again, this is a machine learning approach. So to decode what these voxels are telling us, we're going to build an SVM, which is here, right? So we have, let's call this group A and group B. What's going to happen is we're going to construct what's called a linear hyperplane, and which is the kind of function of the support vector machine. And these guys that live on the line here are support vectors. And what the hyperplane is going to do is just maximally separate group A from group B. And this is a really beautiful example. Unfortunately for us, real world examples are almost never this clear and concise. But there's things we can do to make it easier on us. So two important functions we'll call from the classifier. Fit is going to quote unquote learn the parameters of the model from the data, and predict is going to estimate which category the target belongs to. Was the participant looking at a face, or was he looking at a cat? These are the big questions we have to ask. So notably, we can't predict on the same data that we use to fit the classifier parameters. That would give us a really great result, but it's akin to me sitting down and writing a test and then being thrilled that I aced the test 20 minutes later. It's we all have good days and bad days, but I would hope that I could ace a test of my own design. So training and testing the same exact set of data is unwise. So we won't. So let's just go ahead. We're going to import this classifier, and we're going to fit it with a linear kernel to our mask. And then let's just go ahead and check out. We wouldn't want to use this data in real life, but let's just see what it would print on the entire data. So our classifier obviously did a great job since we're not training or testing it. This is just the data in a vacuum. But you can see here, the first 10 or so scans, the classifier detected to be a face target, I should say, and the next 10 or so was a cat target. And we end up with 216, which, if you remember, is the same number of runs. So that's perfect. We're in good shape here. Yeah, and again, it looks good, but does it mean anything? Unfortunately not. To obtain more meaningful results, what we need to do is split our data into testing and training components. So we're not testing an algorithm on something that it's also been trained on. So we're going to do something called k-fold cross-validation. I like to imagine this as just folding a blanket. Okay, so we're going to take our entire data set and just fold it into a training and test split, fold it again into a training and test split, fold it again into a training and test split, et cetera, 5 times, which will give us really a more accurate estimate of our classifier's performance on the data. So we're just going to run a for loop and just print the accuracy outcomes here. And it looks like fold number 4 was kind of a bummer, but the other 5 seem to do pretty well. So, on average, we're predicting upwards of 76% of the targets to be face or cat, which is, halfway decent. That's pretty robust. So the last part, and this is my favorite part, is taking the coefficients, so taking the outcomes from this classifier and projecting it back into the brain, visualizing that. Because I think that's the coolest part of all this. So what we're going to end up with is a value per each voxel, which is going to be a beta weight coefficient, excuse me. And these are discriminating beta weights. So we're going to look at the absolute values, but essentially a stronger coefficient suggests that that voxel is more tuned to either face or cat targets. And beta weights closer to 0 are less significant in predicting which target the participant was viewing. And thanks to Stanford's very own Russell Poldrack for this great article on region of interest analysis in fMRI, which I found pretty illuminating and helpful in writing up this vignette. So let's just take a look at the first 5 coefficients. Okay, those all look good. And we end up with 464, which, like we said, is the number of voxels of interest for us. So let's just drum roll, please, and see how it looks in the brain. And voila, looks pretty good. So yeah, you can see that voxels that are a darker color are more, the magnitude is more significant. So those voxels tended to be more predictive, and those that were more of a yellow color were less predictive. So thank you for enduring that marathon of information with me. The next slide here just has some resources, places to learn Python. There's a ton of freely available resources out there, but I just wanted to share a few. So I didn't actually start programming until I got to grad school. Like I mentioned, I didn't have any experience, and started with this boot camp from Jose Portilla, who's a data scientist and engineer. And like many programs and courses on, I don't know if it's Udemy or this website here, it's got a very high list price, but it's almost always on sale. So, for $12, you can get a really robust kind of walkthrough of Python. Code Academy I found to be really great as well. I'm actually currently enrolled in their computer science career course, which has been really great. I have to imagine their standalone Python course is really great as well. And then if you were looking just to kind of explore Python and didn't want to commit any monetary asset to it, Google for Ed has a really good Python class as well. And that's all I got. Luiza, do we have any questions?
Yes. So we have a question. What statistics programming tool do you recommend for conducting research that makes quantitative and qualitative methods?
Well, I should be transparent in saying that I use R for statistical analysis. I tend not to use Python just because I think that R is, what's the right word? A little more optimized for stats. In other words, there are fewer steps you have to take in R to get to the point where you're fitting a model or looking at frequency or distribution scores or what have you. There's nothing native in Python that does that, unfortunately. So, you have to do, you have to import packages, you have to, write functions and things like that. It's just a little more, it's a little less optimized for that, I would say. So I would recommend R for stats, but like I said, I mean, Python is more than, usable in that sense.
Yeah, and I would say like it really depends what you mean by qualitative research. So in our lab, we've been doing a lot recently of like work that has to do with natural language processing. Um, so for that, yeah, you can like the person who collaborates with us mostly use Python for to run the word embedding models. But as I said, I know that there are packages that will do that as well. So it really depends what kind of qualitative research you're talking about. Like if you're talking about like reading text as like a human and like joining like different interviews and things like that, um, versus like if you're running like a model to predict how language has changed over time and things like that. But I feel that I will like just second what Ian said. I had much less exposure to Python than he does, but I use R for statistics. But yeah, it's just Python is a more general language, so if it includes things that you wouldn't be able to do like like with like you have to build a software for your like qualitative data analysis for like data input, for example, where people will like go to this website and fill out something, then you wouldn't use R for that. But for analyzing it, R could be a good candidate.
Yeah, and I mentioned the Twitter bot just kind of as a fun aside, but it's actually a pretty good illustration of how easy it is just to build something and put it on the server. I don't think anything like that really exists for R scripts. I use Python Anywhere, and it's like $5 a month, and you can put as many things on a server as you want, and they'll execute it at a time of day. It's super useful and really easy to do. So I think that's a strength of Python, I would say.
Yeah, that's great. So that's all the questions we have for now.
Cool.
Yeah, happy to wait if anyone else has any questions that they would like to share, anything that wasn't clear or they're curious about. But yeah, but if not, it was a pleasure to talk a little bit about R with you guys today. I hope both of us kind of showed you some evidence that it is worth learning the learning curve of these languages to test the waters a little bit. There are a lot of great free resources out there for you if you're interested in learning, and we're going to share the resources that we showed you today. Okay, so we have one question coming in. Have you used Form R for online surveys before? I'm trying to decide if it's worth learning. I have not heard of Form R before. Ian, have you?
No, I never have.
You guys are killing it with all the different tools that we've never heard of. Yeah, I think so. Yeah, I haven't heard of it before. Cannot really talk about if it's worth the learning curve. But yeah, the tools that we're talking today are just so general that like I feel that could be one way of identifying things that are worth the time to learn. If you think that you can apply it to many different things and it would be useful going forward. I feel that these tools, like if you're in the pre-graduate school stage or you're applying to a PhD program, and maybe that's not what you're thinking about right now, but it does save you a lot of time in graduate school if you know a little bit about them before starting. Do graduate school classes teach R and Python, or is learning done in your own time? So Ian can talk a little bit about his master's experience and my PhD experience so far. We do have one class that was, well, two classes that were conducted in R. I will say that the time spent teaching people to use R was fairly short. Like I have one friend who came with no R experience, and she struggled a little bit like the first couple of weeks to just like get started. So that's why I'm saying that like sometimes it helps a lot for you to do it, some of the learning on your own time. But I do think that most programs will give you at least like a couple weeks of intro if you have not, because most programs won't assume that you know it straight off the bat. They will give you, and depending on the program, you can also like our program has a lot of flexibility that like so I took like a data science class last quarter, well actually in the spring, in the winter. And that was really great, and it wasn't in the psychology department. I just was able to take a class offline. So learning can be done in your own time. You can also like search for resources outside of your department if your graduate program is okay with that. where you can give more of like in-depth experience into learning these tools?
Yeah, my experience at NYU was similar. So my first semester of my first year in grad school, you have to take experimental stats and analysis and that kind of thing, and that was all in SPSS. When I started doing lab work with John Freeman's lab that fall, it was all in R and a little bit in Python. So uh, I would say that universities are probably trending more towards having these things available. They're not there yet. Like my last semester of grad school this past spring, I was in an intro to machine learning class, which was the first time that NYU had taught that, and it required coming to the table with some knowledge. It wasn't like an introduction to Python class, but yeah, I mean, broadly speaking, my guess is that universities are going to start moving in that direction where those things are more available. Because I think one thing we didn't really talk about is how useful these are, even if you don't want to go to grad school. The job market, if you're applying to industry jobs and you're interested in that kind of work, and you can code in Python or R or both, I mean, you're putting yourself in a very good position. Those are really desirable skills to have. So yeah, long answer, but my intuition is that schools are probably moving in that direction if they're not there already.
Yeah, for sure. Second that. I think that, learning R also just gave me a good way of like, at first I realized how much I like it and how much I like data analysis and doing these things, which helps if you also are considering a career in industry afterwards. Like, there's really a lot of space for people who have these skills. So we have another question. I'm sure this is fairly lab dependent, but one of the PhD students I talked to said that certain programs prioritize certain statistical programs like M plus instead of R. Would you say that the Stanford Psychology Department has a general preference? So I would say it kind of depends on the sub area that you're in. If you're doing a lot of like neuroscientific research, I feel that people still use like MATLAB a fair amount. So it's really going to depend. I think one way to gauge interest from like your PI is just looking at like, yeah, like their papers, like what tools do they say they use. So the department as a whole does not have like a strict preference. I think that R is pretty much the thing that they would expect and most people have some exposure to. But if there's anything beyond that, it's going to be, as you said, a little bit lab specific. And in my experience in applying to other programs, that was the case too, where like, I think like, yeah, either R or Python are things that, like people really value. I don't think anyone would be disappointed if you said that you knew Python and not like M plus, unless that's all they use, and that for them, it would be kind of like a barrier for collaboration if you didn't use the same package. But yeah, but I feel that these two tools are just so general that they're yeah, I can't think about labs that would be that would think it's a disadvantage to know them.
Yeah, I would agree with that for sure. And it's also very domain specific. So I remember reading an analysis of what's the right way to put it? Job prerequisites per geographic region. And R was really popular in Washington, D.C., but Python was really popular in San Francisco. So like what's the difference there? It's like, political science versus computer science. So the domain, the context that you're working within is really important as well.
Yeah, for sure. And I think that you will definitely find people on both sides that think like the tool they use are like is the best tool ever out there. I told Ian that the class that I took was really, they really try to imbue this idea that like R is like the best thing in the whole world, which I do think that it convinced me partially. I do think that like a lot of the things like that R can do, I had no idea that it could. But I will agree with Ian that Python is a general language. So there's more that you can do outside of statistics.
Mm-hmm. So it looks like apart from R and Python, what other general statistics tools do you know that are important in academia? That's a good question. What do you think?
Yeah, I think, again, this really depends. I feel like SPSS is still widely used, especially by older faculty members. Like learning coding language, as we talked about, it can be a steep learning curve. So some folks who know something, they just like grab onto it. So I wouldn't say it's like an important thing for you to learn if you don't know SPSS, but I just wanted to say it's prominent out there. MATLAB, I think, is the one other thing that comes to mind as that is really widely used in like neuroscience research, even though it's proprietary. So there's kind of like that barrier for entry. Yeah, I feel that
And
these
even
two are really great tools. So like they really cover a lot of space. But Ian, do you have any?
Well, I was going to say, I mean, even in my work at NYU, I mean, we were doing a lot of MVPA and more nuanced approaches to neuroimaging, and I never learned anything in MATLAB. I think I tried to once, and I maybe halfway through the video I was watching, I was like, why am I learning this? I can just do it in Python. So the tools are out there, and the packages are out there. So to answer this last question we have in the stack, it looks like I've never had any reason to use MATLAB. People who use neuroimaging design a little more nuanced than I do use MATLAB very heavily, but I've never had to personally.
Yeah, I think if you specialize well enough in one of these languages, you can kind of adapt it for the tasks you want it to do. So yeah, so I think that we can, as Ian said, if you have a pretty good knowledge of Python, you can kind of do a lot of the MATLAB things in Python.
Oh yeah, and I'm seeing here one of the researchers in our lab actually only uses Python because so many of the libraries are already written. So most people use Python now, is what I'm seeing. So
Mhm.
uh, yeah, good to know.
Yeah. Okay, great. So I think we've answered all the questions. Thank you so much for joining us today. I hope this was useful for y'all. Yeah, we'll send an email with all those resources. Feel free to, ask some questions if there's anything lingering after this talk. Feel free to reach out to us.
Thanks, everybody.
Thank you.